Hello students, welcome back. In this video we are going to go through Chapter 10, Section 3, Prediction Intervals and Variation. You should also know that we are going to skip Chapter 10, Section 4, and Section 5. So this is the last section of Chapter 10. You are welcome. Okay, so the key concept here is we are going to introduce prediction intervals, which is an interval estimate of the predicted value of y. So it's just basically a confidence interval for a predicted value of y given a scatter plot once we find the regression equation. So it really actually, in my opinion, isn't introducing too much of new information. So prediction interval is just the range of values to estimate the variable, in this case y. So it's just another confidence interval for the parameter. So our objective is to find that interval with a lower limit and an upper limit saying, okay, I'm 90% sure that the actual value of y will fall between this lower limit and this upper limit given an x value. Okay, so for each fixed value of x, so that's what we're kind of estimating. Think back to the last section where I said, okay, what if we had 10 kilograms of chocolate that was consumed? What would be the expected y value? So for each fixed value of x that's going to be given, the corresponding sample values of y are normally distributed about the regression. So that's a requirement here. So what do I mean by that? So the x values are fixed. The y's are normally distributed around the regression line. So that means that if you were to plot the distance of these y values from the regression lines, they would be normally distributed. You'll have some that are really close, some that are further away, and that will be generally a bell shape if you were to plot it. So just remember, y hat is the predicted value, and then y is just the actual measured value. Y uses the actual blue dots for the actual data values, and then y hat is the predicted value using the line of best fit. That would be the red line. So how do we find the values? We have to use the formula. Same formula as before, now we're just using the parameter of y's. So given a fixed and known value of x naught or x of 0, the prediction interval will be given by this. So it's the y hat minus the margin of error is less than y, which is the actual, which is less than the predicted value plus the margin of error. How do you figure out the margin of error? It's given by this beautiful equation over here, which again you're not going to have to solve yourself, but you should know where it comes from. And x naught is a given value of x. T of alpha over 2 has n minus 2 degrees of freedom, and then S of E is the standard error of estimate found on the next slide's formulas. So here are your formulas for getting that S value that we're using over here. Okay, once again, you will have to do these by hand, but I want you to at least get your eyes on them so you know that where they come from and where they exist, just so you're not reading an answer off of a calculator and then just working with it. You know, in theory, where the number is coming from and how it was calculated. So, without further ado, let's go back to our lovely example of chocolate and Nobel Prizes. Finding a prediction interval. So, for the paired chocolate and Nobel Prize data previously used, we found that there is sufficient evidence to support the claim of a linear correlation between the two variables, and the regression equation was given by y hat equals negative 3.37 plus 2.49x. So, if a country has a chocolate consumption amount given by x equals 10 kilograms per capita, find the best predicted value of the Nobel Prize rate. Then use a chocolate consumption amount of x equals 10 kilograms per capita to construct a 95% prediction interval for the rate of Nobel Prizes. So we want to know, with 95% confidence, what is the range that y value should be. So if we substitute x into the equation, part A, we can get that y hat equals 21.5 Nobel Prizes per 10 million people. That is what we expect, or what we're predicting that we will get. The next is we are going to create a confidence interval. So once we use a technology, the 95% confidence interval shows us that we are within this range. Since your computer doesn't want to, or I should say your textbook doesn't want to show you how you got that, I had to add that section. So the step-by-step solutions, or not solutions, the step-by-step procedure for how to do a confidence interval is shown on page 508. And here are the steps. So first, go to StatCrunch, and then enter the chocolate values for variable 1. Step 2, enter the Nobel values for variable 2. 3, press stat, regression, simple regression. 4, enter variable 1 for x. 2, enter variable 2 for y. And then step 5 is the prediction value of y, have that be set to x values, 10, and the level 0.95. Just to show you what that looks like, here is your variable 1, variable 2 typed in. Once you're here, have your variable 1 be your x variable, variable 2 be your y variable. That's a mistake right here, so make sure you note that variable 2 is your y variable. Then when you go to perform, confidence level 0.95, and then for the prediction of y, have your x value be 10 and your level be 0.95. You don't actually have to do this previous step, but just go make sure this is accurate. Let me say that again. I feel like I don't like the way I worded that. X variable, variable 1. Y variable, variable 2. Go down to prediction of y, x value of 10, level 0.95, hit commute, you get this value. So here is your confidence level right here. You're 95% sure that the true value of y will fall between 7.79 and 35.33. Okay? You can also calculate this by using the hand calculations as well. Why you would, I don't know. So the interpretation is that the 95% level is between 7.8 and 35.3. So it means that if we select some country with a chocolate consumption rate of 10 kilograms per capita, we have a 95% confidence that the limits of 7.8 and 35.3 contain the Nobel Prize rate. Now that's a pretty big range. I mean, 7.8 to 35.3, that's a huge interval. So, but that's just because we only dealt with 23 pairs of data values. In actual practice, we would want much more, but you get the idea. So now we're going back to the explained and unexplained variation, which basically says how much of the value can be explained by the correlation and how much cannot be. So assume that we have a sample of paired data having the following properties. We're looking at this over here. So, looking at these bullets, there is sufficient evidence to support a claim of a linear correlation. Assume that the equation of the regression line is given by y hat equals 3 plus 2x, so nice and simple. The mean of the y values is given by y bar equals 9, and one of the pairs of sample data is 5, 19. So, the point 513 is one of the points on the regression line, because if you plug 5 in for x right here, 2 times 5 is 10, plus 3 is 13. So that would be one of the points on the line. But we know that a actual pair is 519. So there's going to be a residual gap right there. And we know that the mean of y is 9. So what do all those three things tell us? Let's look at this graph right here. This straight line right here, that is your mean. The mean is y bar equals 9. So if you were to graph y equals 9, you have a straight line right here. This magenta looking line is going to be your residual equation. It's y equals 3 plus 2x. So your initial value, your y-intercept is 3, up 2 over 1, up 2 over 1, so on. So if we were to look at where x equals 5, we have 3 points right here. 5, 9 is where it crosses the mean line of y equals 9. 5, 13 is where it crosses the expected or the predicted value. And then 5, 19 is what the actual measured data point was. So we say that the unexplained deviation is going to be the difference between the actual and the predicted. That's the unexplained. The explained deviation is going to be the predicted minus the average y, or y hat minus y bar. The total deviation is going to be the sum of these two gaps, or just the difference between this upper and this lower value right here. So if you want that in equation form, here it is over here as well. So the total deviation is the vertical distance y minus y bar. Y is up here, y bar is down here, and this value is the y hat value. Okay? So that's your total variation right there. And your coefficient of determination is the proportion of the variation in y that is explained by the regression line. So that's r squared again, which is the total, or it's the explained variation divided by the total variation. So we did this example before. If we have an r value of 0.801, the coefficient of determination is 0.642, which is r squared, which means that 64.2% of the total variation can be explained by chocolate consumption. But the complement of that, 35.8%, cannot be explained. So that 35.8 is explained by some other factor or random variation. It's not because of the chocolate. Of course, disclaimer, we know that by common sense, it's pretty silly to think that their Nobel Prize amount is affected by chocolate consumption. So that's just, again, the central theme of correlation does not suggest causation. And that concludes Chapter 10. Any questions, please email me.